tell me in one line that what is really a machine learning?
Machine learning is basically like some algorithms for running something specially, or maybe intelligent algorithms or something like that.
Okay, and that's a really vague definition of machine learning. So basically, what machine learning do for you is it creates a mathematical model for any input and given output. So it tries to find a relation between input and output set of data. So now what is the set? So set can be this mathematical input like number, integers, or regression type inputs. So it tries to find a relationship. So what it basically does for you is find a mathematical function that takes domain x and output result y. So it's kind of function fx that results y. So this is what a machine learning do for you. Now, uh, if you have heard about neurons, so like neurons, how it work, uh, our brain is also made up of billion of neurons, right? So neuron actually works like it takes some signal from the environment, process it, and then produces some output, right? So and this is exactly the this is exactly what how the real neuron and the machine learning or the artificial neuron works. For like in machine learning, we have this almost the same model of neuron, and there's a neuron. It takes some input x. Input consists of uh, several signals that is coming from different devices or different environmental factors. So it can have n number of inputs, and then it formulates or it operates some mathematical functions over those input and produces some or output y. So basically neuron is an input and m output terminal device, and this neuron has a capability of learning. So once this neuron has a capability of learning, it can generalize functions, and if it can generalize functions, then obviously it can do things which basically, if it can generalize function, you can say that this neuron is has a learning capabilities. So now how a neuron learns something, and that is where the machine learning comes. So uh, you know that neuron takes an input and produces m output. So if we talk about really simple neuron, so what it does is it takes an input multiplied with some weights, and like each neuron signal is multiplied with some specific weight, and then some add them all and produces some y. So let's see how the real neuron, like which is present in our brain, actually works. So if you know the perceptrons, so have you heard about what is perceptron?
Nope.
So so okay, wait a second. So this is the image of real neuron that is present in our brain or any organism's brain cell. So this is building block of brain cell. So this is real neuron. It gets the signal from here. Okay, image is sharing, right? So yeah, it gets signal from here, and then all the signals are multiplied with some weights. So so the distance between the receptor, this is actually called the receptors. So distance between receptors and the other signal actually causes the effect of weight multiplication. So all the weights are get added up, and then here some processing are done, and then signals are transferred to other neurons. So this is how So this is how the real neuron works. But when we talk about the artificial neurons, so actually we can't have lots of complexities there, because you know that machine learning is already very computation expensive. So we try to develop our approximate neuron model. So it was given by some scientists around in 80s or a lot ago. So and the basic the basic model of neuron says that it takes some input. Say it has three inputs: x1, x2, x3. Okay, each input is multiplied with some given weight w1, w2, w3. So and then added up. So x1 w1 plus x2 w2 plus x3 w3. It gets added up. So this is your weighted sum of all the input signals. Then this weighted sum is actually act as a firing parameter that neurons should fire or not. So we have a function that is activation function. Activation function decides whether the neuron should fire, right, whether the neuron should fire or not. So it takes this value x1 w1 plus x2 w2 x3 w3, and then it converts this value into 0 1 function that either the neuron should fire or not to fire. So there are various types of activation function. For example, one of the really basic function is logistic function. Then we have sigmoid function, tanh function. So once this is your tanh function. So it takes the input. You can see that it has a domain over all real numbers and range of -1 to 1. So it takes that weighted sum and produces an output between -1 to 1. And this -1 to 1 value then go to the second input to the second neuron, and so on. So now how this is how the neuron gives you output. So this is actually called feed forward mechanism. It takes the input and produces the output. So you just see that how the neuron produces output, but it is not learning anything right now. So how the neuron really works, or sorry, how the neuron should really learn anything. So there's something called back propagation. The back propagation makes the neuron to learn new things, and here the learning implies minimizing the error that is getting from output of neuron and the real values. So what we do is we give the input to the neuron and produce the output, and then we try to match this output with the real output that we want. And we want to minimize the error between the output of neuron and our own real output. So that is a real output r, and the output produced by neuron, that is y. So we want to minimize the value r minus modulo of r minus y. So to minimize this, what we do is, and there are several different mechanisms to minimize this error, but the most famous one is gradient descent way. Yeah, gradient descent actually is a gradient descent is basically try to find the error, change in error with respect to the internal variables, and then manipulate the internal variables to minimize the error. So you can see there's a curve here, and this is the initial say initial weight or initial parameters. What we do is we try to find that whether it should go downward or upward. So through some mathematical operators, differential operators basically. So we try to minimize it by finding the direction through finding a direction where this weight should move. So you can see that this, if this is a parabolic like shape, and this is the initial weight. So if the ball rolls down to here, then the error will minimize. So This is exactly what we do in gradient descent. We try to find the weights that would minimize the local values. So, gra- so machine learning try to optimize. So machine learning try to optimize the initial weights of the neurons, so that the output of neurons produces less error. That is modulo of y minus e, or y minus r. So it tries to optimize that thing. Now the next thing is, this is actually called the back propagation. We take up the output and find the gradient descent and manipulate the internal weights to minimize the error. Now, this is the overview of neuron, how actually the neuron works. But the problem with the neuron is, if you look at the mathematical model, what we do is we find the weighted sum. So this is a linear system. So it can only generalize the linear functions. But do we have all the functions in world linear? Do we have? No. Like, if we even take the trajectory of a ball rolling on, say, plane, it has a degree 2 equation. So we are not really concerned about the linear function. We want some really complex function to be get generalized by the neurons, because we can generalize the linear function by ourselves. So we want the neurons to do some really difficult work for us. Like, if we take the example of, say, image recognition. So image recognition have lots of things. The edge analysis, we try to find the edges, and then we want to find the relation between edges. Say in the handwriting recognition, we want to find the edges that actually correspond to some character. Like u has a like parabolic like shape, and o has a circular like structure. So uh, machine, and this can't be done with a linear neuron or any linear model or any linear system. So the next thing comes to machine learning is the architectures. We try to arrange the neurons one over another, or we connect lots of one neuron to another neuron, to uh, to increase the output, to increase the complexity of output by generalizing higher degree functions. Because one neuron can do a linear function. If we cascade one neuron to another neuron, it can generalize higher degree of polynomials. So we keep on cascading neurons to produce higher degree functions. So this is here comes the first simple architecture, that is multi-layer perceptrons. This is the example of multi-layer perceptron. Circular object here is actually a single entity of neuron. So we have three neurons here, then we have four neurons here, and two neurons here. These are called input neurons, these are called output neurons, and all the neurons in between input and output are hidden neurons. So this is actually the single layer of neuron. This is second layer, first layer of neuron, second layer of neuron, and third layer of neuron. You can see that when we keep on cascading neurons, and it increases the internal complexity of weighted sum, and finally we get a non-linear function. So this neuron can generalize a non-linear function. Now the simplest example of uh, why we really need a non-linear function. If you have heard about logic gates, so are you guys aware of logic gates, right?
Yeah. Yes.
So okay, name any few.
And or
Okay, so first is and. So and has a logical truth table, and logic truth table. So here we have the AND table. So you can see 0 0 is 0, 0 1 is 0, 1 0 is 0, and 1 1 is 1. So if we plot it on a, say, graph, what the heck? So 0 0 is 0, 0 0 is 0, and then 0 1, 0 1 is again 0. Whatever. 1 0 is again 0, and 1 1 is 1. So I tried to plot. Okay, my bad drawing. So I tried to plot the truth table on a map. So each red represents the classification to 0, and green represents the classification to 1. So 0 0 is 0, 0 1 is 0, and 1 0 is 0, and 1 1 is 1. That is green dot. So if I want a neuron to learn this, a single neuron to learn this, what it can do is tries to find a function which can separate these two. So what it can do is it generalize a linear function that are equation of line, and all the points that are below this line are red dots, and all the lines that are above this line is green are green dots. So it can generalize a AND gate, logical AND gate very easily uh, through a simple linear function. But what if we talk about other functions like or okay, or can be done the very similar way, but what about the XOR function, XOR? So if we look at the XOR function, this is red, this is green, and this is green. Is there any way to separate green dots with red dots by single line or any linear function? Is there any way?
No.
Yeah, we can't separate green dots from red dots by a single line, so that we can say that all the dots which are above that line is green, and all the dots below that line is red. So this function can't be generalized by a single neuron. So yeah, we can't really create a logical XOR operation with a single neuron. Let's see. So this is XOR function, right? Zero. Okay, it's something different. No, same. 0 0 is 0, and 1 1 is 1. So, and I'll take two inputs. Okay, only one neuron. Now I'll see that if it can generalize or not. Wait. Okay, it's AND operation now. It's and. Okay, this is XOR. Let's see. So it's already 156 iterations, and we have still a loss of 41%. That's really lot, even in test. So, training loss is around 38%. So if we keep on going, no, no good luck. So you can see that a single neuron is incapable of generalizing a XOR type function, because what it can do is it tries to find a linear function, and we know we can't separate the green dots, blue dots with orange dots, this linear function. So what happens when we cascade neurons? So okay, I cascade a single neuron with a single neuron. So I have two layer of neurons, two hidden layers. And let's see what we can do now. Earlier it was something 48 now. So it's now 41%. Still no good luck. No luck. So here it is a linear function. Again, it is a linear function. But if we increase the neurons here, Then two linear functions goes to a single neuron and tries to generalize some more complex function. So if you look at this, it is as yeah, this neuron is able to find a function which is non-linear. This curve is non-linear, right? So, and it has a training loss now 35%. So yes, we actually optimize the output. What we increase the neuron. Great, it's 18% now. 29%, and it's 4% now. So the main idea is if we keep on cascading neurons, obviously logically we can't do brute force over that. So we need some logic to cascade neurons in order to optimize the output. And optimizing the output means minimizing the error rate. So you can see that from 41% we are now on 3%. So it's really a lot. So this is how the multi-layer perceptrons work. Where it is. So this is the structure of multi-layer perceptron where each neuron is connected to every neuron in the previous layer. So it's a complete graph. So this idea really works. It is a really simple architecture, but it works really great. Like even Google uses for image recognition. But now the problem with the image recognition is, if you look at any image, say, I have any good image here. Let's take a wallpaper. What is the difference between a normal recognition and image recognition? So if we look at this image, so if we look at this image, basically, images are not random in real world. They are every pixel, if this is red pixel, yeah. So if this is a red pixel, then it is actually not randomly set to red. It has some meaning over the reference or the local frame or to the neighbors. So each pixel is actually related to its neighbor. And the problem with the multi-layer perceptron is that it connects all the pixels to every other pixel. But we know that that the pixel which is present here is not going to related to the pixel which is present here. Obviously, it will not anywhere related to this pixel. So the problem with the multi-layer perceptron is it increases the complexity of computation. It has lots of connection, and each connection itself find the linear function, so it increases the computation. It can find the it can actually find the it is good for image recognition, but thing is the computation power. So there's a new architecture for that. What it do is it use this property of images, that all the images are locally connected and not the globally connected. That is, images which are pixels which are present here are not going to relate to the pixels which are uh, present here or here. So we use the local reference, that this pixel is related to only pixels which are present here. So this is actually called the convolution neural network. It has been developed. Uh, it has been developed on actually inspired from. It has been inspired from the human eye and the organisms. So it actually connects the local pixels to the neurons and not the whole image. So it actually reduces the number of connections in the multi-layer perceptrons. So see, uh, only locally referenced images. Yes. So only locally referenced images are, why was he repeating? So only locally referenced images are connected to a single neuron and not the whole image. So this causes to reduce the number of connections and hence the computation energy or computation we need for finding a relation between the images. So this actually really works great because we have less connections, so neurons are able to generalize really fast. And if it is able to generalize really fast, then obviously it can uh, optimize the output. So convolution neural network is good for image recognition or locally referenced pattern recognition. So we just saw how the multi-layer perceptron works, how the convolution neural network works. So these are actually really basis of machine learning. Problem with machine learning is the optimization. We try to optimize the error uh, that the neuron or the architecture makes over subset of inputs. So the problem with the these idea is the uh, function that we are going to generalize. Like not all the mathematical function have uh, global maximum equals to local maximum. So if we, okay, I don't have any example here. So problem with that is when we set any initial weight, we actually use the random initial weight matrix. So when we set a weight matrix, the neuron tries to optimize it using gradient descent. We just saw that the gradient descent work like the rolling of ball over some inclined plane. If we have something like this function and we are say here, and the gradient descent could make it to here to optimize the error rate, but we know that globally there is one more minimum that is here. So this is really a main problem with the optimization. We can find the local maximum, local minimum, but we can't find the global minimum. So the idea is we try to use various methods to reach to optimize local minimum. So those ideas are, first thing is momentum. So okay, some really basic. So the initialization of initial weights. So if we initialize the weight matrix to random, so sometimes we appear here initially, here. It can be anywhere. So what we can do is we train our model over several initial weight metrics, and see the minimum error that we reach. And this is and yeah, if initially we were here, then a neuron could reach here using gradient descent, but it can't reach here, right? And say if the initialization was from here using the random function, then we can reach to here. So we try to use different epochs, different training initial weight metrics to find the best local minimum we could go. Okay. So yeah, this is the problem with the gradient descent. Okay. So, machine learning suggestions. See, one thing with one thing that is really problem with doing the machine learning is the computation power that we need to achieve something in machine learning. Like if we talk about the things which are big enterprises are doing right now with machine learning, like Amazon is doing Amazon Go, so using computer vision and all. So what they are doing is taking the convolution neural network and then finding the pattern, then trying to recognize the faces and predict the items that the people are taking and all. So the all these stuffs need a lot of computation power. We can't actually do all those stuff on our uh, obviously local computers. So the thing is, if anyone wants to start with machine learning, the first thing is really go with some basics ideas. Like I talked about the gradient descent. So check on internet how the gradient descent works, and how the gradient descent works. What are the problems, issues with the descent. So I'll list. I'll okay. I discuss one problem with the gradient descent. So you just saw the gradient descent finds the uh, tries to predict the direction of the weight matrix, change in weight matrix. So the problem with the cascading of neurons is if we keep on cascading the neurons and find the differential or the apply the gradient descent over it, the error starts to diminish because we have a fixed precision in the computers. Like we can't on C language, we have only 12 bits or 16 bits for the precision. So as we keep on cascading the neurons, the error rate diminishes. Like we are not significantly able to track the error. So this adds to the adds to what the basically the great it it so as the error rate diminishes, we are unable to find the gradient descent properly. So this causes one problem, and there are lots of other problems, that the exploding of gradient descent. If gradient descent is greater than one, and we keep on cascading the neurons, it gets multiplied and multiplied. So it explodes it because we have a range over the integers, or the floating points in computer. So all these problem adds up to the problem we face in computation. Uh, so if anyone wants to start, so first go with the mathematical model of all the machine learning architectures, and how these maybe do some mathematical derivations on of all the gradient descent, and the activation function, feed forward mechanism, back propagation. So you can find all these stuffs in books actually. There's a nice book. Uh, what was that? What was its name? Algorithmic Perspective Machine Learning by Stephen. Wait a second. By Stephen Marshland. So this is really a nice book. It has some really insight over the mathematical idea and all the stuffs which I discussed. So this is one thing, and yeah, the second thing, of course, I just said that it has lots of computation things that we need to get really nice things to do with the machine learning. So other idea is try to do some creative work using try to find or exploit some creative ideas using machine learning. Like if you have seen the T-Rex. Are you aware of T-Rex game? Chrome T-Rex game. Yep.
Yes, yes.
So I created a actually T-Rex game player. So it actually I could show you. So this has been so I use multi-layer perceptron here. So what it actually plays this game, and it has reached a highest score of around what 10,770. This is really great. So a machine learning algorithm which learns this game and then play this. So this is a really creative idea to application of machine learning. So to practice your machine learning abilities, one thing is find the creative application and work over it, and the second thing is just go over the mathematical model and learn the stuffs. Let's see. Oh, initially it's make some random guesses and then see what works best. Okay, bad guess. I hope it had learned data. Bhai. So actually it has also the same random weight matrix. If I refresh, then it will have the different weight matrix. Maybe it will work this time. Great. Let's see. क्या मजाक है. Okay. Okay, it has learned the game. No, see, it is able to predict every move perfectly. The main idea is same, the multi-layer perceptron and stuffs. Anything else? Also, you can tell us what you are currently working on. Okay, actually, I'm working on some stuff like operating system project, and yeah, my side work on machine learning. Like I do keep on researching on. Yeah, right now I'm studying the genetic algorithm. So yeah, if you want, I can discuss the genetic algorithms.
Yeah, maybe some other.
Any question like on machine learning or whatever the stuff I discussed today?
More about what is weight, what you define as weight matrix, that part.
Okay, yeah, weight matrix. So I discussed the thing that input values are multiplied with some w1, w2, w3. So w1, w2, w3 is a weight vector, right? For a single neuron. When we cascade neurons, so we need different a lots of weight vectors. So we compress all these weight vector into a single matrix. So first column is for neuron 1, second column is for neuron 2. So this is a weight matrix. So what we do is we can initialize this weight matrix because we need some initial weights. So we can initialize it with any random values, uh, and then we see what works best for the neuron architecture. So this is the weight matrix.
Thank you, Aman. So
Okay,
yeah, thanks.
thanks.
Yeah, like